Hello. So, in this video we are going to be talking about the rigid translations, and in particular we're going to be looking at that analytic view. So we're going to see the sort of nuts and bolts of how it works. Okay, so rigid translations. So if we have some curve, right, if you remember, rigid translations are when we want to take that curve and we want to move it in a sort of direction, but it needs to stay rigid, meaning that it can't sort of warp or turn or stretch or any of that stuff. So we could turn it, we could sort of move it left, right, for example. So we can move it to the right. We could also, for example, move it downward. But the idea here is that the shape itself doesn't change, just sort of the location of the shape changes. Okay. All right. So how do we do that? Well, one of the first sort of useful observations is that the horizontal and the vertical movement are sort of independent. So we can tackle these things sort of separate from one another. And the horizontal movement, if you remember, right, is moving along that x-axis, which is the independent variable. So if we have some function, for example, like log x, right? So we have this is just used by example. All of this stuff works for any of the functions, to be clear, but just so we have something concrete to work on, let's talk about log x. Well, that x bit, right, that's the independent variable. So that's going to be what sort of controls that left-right movement. And in particular, we want to sort of notice that this x is the part that's sort of inside that parentheses. So if we want to sort of mess with that variable, right, if we want to move that thing and sort of do something in that left-right direction, we want to do it inside those parentheses. So in particular, we want to look at some f of x and then do something to it. And in particular, we want to do that like plus h or plus some number, right? So we might think about this and say, okay, if I want to move this thing left, right, whatever, up, down, I want to sort of figure out which variable I want, right? So if it's left, right, I want the x stuff, right? I want the independent variable. And so I'm going to be adding a value inside. And when I say adding a value, right, I mean any real number. So it could be a negative. So this could be sort of the equivalent of subtracting, right? If I add -3, for example. Okay, so I sort of have this general form. I have f of x plus some number. That number might be negative. And this should move the thing left or right, depending on what number I add. And it seems like this should be the horizontal movement. And in fact, it is almost. There's sort of a catch that's going to happen. And to see sort of why that is, it's sort of easiest to look at an example. So let's say that we have some f of x, and we want to add 3, right? So this graph that we have right here is the original f of x. What happens when we do f of x plus 3? Well, it's going to move it left or right. We might think, okay, well, adding 3, positive number, positive direction, it should move to the right 3. And it doesn't, because of course it doesn't, right? Why not make life harder? So it sort of worked. It moved sort of the equivalent of 3, but it moved it left, not to the right. So what's the deal, right? So we have this f of x plus h. H is the horizontal movement, almost. When we did that x plus 3 bit, we went 3, but we went left, not right. So the reason for this is that if I think about what happens when I add 3, think about like originally we had f of x, and if we plugged in x equals 0, we get f of 0. So in order to get that same value of 0, in order to sort of get to the 0 point, because I'm adding 3, I can't use x equals 0. I'd have to use x equals -3. So in order to get to 0, I have to go left 3. So this is why sort of in reality that I'm sort of getting the opposite of what I'd expect. Adding 3 means that I have to go left. I have to go to the -3 in order to get to where I start. So this ends up doing sort of the opposite of what we would think. So if I'm going to add -3, that would go to the right, even though negative seems like it should go left. So adding -3 goes to the right. Adding +3 goes to the left. So it's sort of the opposite of what we'd expect. In fact, this is going to bring up the mantra that we are going to say throughout all of this process, be it translations, transformations, all of these things, which is that everything about x is backwards. So it sort of works in terms of like the x part does indeed sort of deal with the left-right parts, right? But it's always the opposite of what we'd expect. If we're adding a positive number, it goes to the negative side. If we add a negative number, it goes to the positive side. When we talk about transformations, if we multiply by a big number, it gets smaller. When we multiply by a small number, it gets bigger somehow. So this is the sort of thing that you want to internalize. Everything about x sort of works the opposite of what your intuition would think, okay? For this reason, another way that this is often written, and this is one of those like personal preference moments, is instead of looking at f of x plus h, where if I put in like 3 for h, that would be x plus 3, so it would move left. So when we say h is 3, we're moving left, and that's sort of counterintuitive. We could instead do f of x minus h, so that if I plug in an h of 3, that's x minus 3, and now when I plug in 3, I'm going to the right. But it's because I've sort of switched the sign in advance. So instead of adding a value, I'm subtracting a value, and it sort of makes it sound right, even though it still looks just as wrong. So if you prefer that sort of sound right, even though it sort of looks the same when you have it written down, you can use that x minus h form, okay? All right, so that's horizontal movement. What about vertical movement? Well, vertical movement, that's the dependent variable, right? That's the y value. But importantly, when we're looking at something like f of x is log of x, that value occurs after the function has sort of applied. So meaning that if I want to add 3 to the dependent variable, I would add 3 after I've applied f, or after I've computed the log. And so that happens outside of the parenthesis, right? So instead of having f of x plus 3, it's f of x plus 3. Right? So this is a subtle but really important difference, is that addition subtraction, if it's happening outside of whatever the function is, right? If it's happening after the log or the square root or whatever function is sort of lurking, then it's affecting the dependent variable and it moves up down rather than left right, which is what happens when it's inside the parentheses or happening sort of before we apply whatever that function is. So before we take a log, or before we square root, or before we take, the square or something like that, okay? The good news, though, is if we use this f of x plus k, it actually is the vertical movement, meaning that vertical movement works exactly how we'd expect. So everything about x is backwards, but fortunately everything about the y works pretty much the way we would expect it. If we add a positive number, it goes up. If we subtract a number, right, adding a negative, it goes down. So it sort of works the way we want it to. Okay, so what did we do? We went through the different types of the rigid translation, right? So we talked about the up, down, and left, right. And sort of importantly, when we did the rigid translation left, right, we talked about the x values inside the parentheses. And we came up with that mantra that everything about x is backwards, right? So this is something that'll come up again when we talk about the analytic view of transformations, but that's sort of one of the key takeaways here. Everything about x is backwards from what you'd think. And yet, when it comes to the dependent variable, when it comes to the up-down movement, the y, everything works the way that we'd want it to work. So the y stuff, good. X stuff, backwards for annoying reasons. Okay? So that is that.